Hello, I'm Rod Elmore, and today we got kind of what I find a very interesting topic. It's polar coordinates. And I find it interesting because it's one of the few times, or the first times, that we get away from rectangular coordinates. We find out there's a bigger world out there than just doing everything in rectangular coordinates. So let's take a look at this. First, I want to develop the relationships, but also if you can see where it came from, every problem we do will be fairly simple. But if you don't understand it and you're just going to memorize it, it can be a real chore. So try to think, can I understand that? And the answer to that question of can you is yes. It's very simple. It's just new. So let's kind of review regular coordinates. If you look at regular coordinates, what we did is we said this was our x-axis, this was our y-axis. And if we had a point out here, say a point at that place, what we said was that this had coordinates of x, y. And what did that mean? That meant you went over x and up y. Over x and up y, because we said the first number in our ordered pair of numbers was the horizontal or the x values or input. The second was our vertical values or our output. So if this was like 2, 3, we'd go over 2 and up 3. But it's x, y, so we're going to go over x and up y. So this is our y over here also. So now what is another way you could get to that point? Because there always was another way. But this is kind of like if everything was in blocks and you go 2 blocks this way, 3 blocks that way. But what about the way a bird would go? Wouldn't it be easier to go from here straight up to that point? Wouldn't that be an easier way to go than to go over x and up y? And of course, that's the answer. Let me straighten that out. Our bird was a little bit woozy that day. Maybe it won't be much better this time, but maybe a little bit. So we're going to go that way. So rather than tell somebody to go this many blocks this way and then that many blocks that way, we're going to say, we're going to pick this angle, and then we're going to tell them how far to go out on that. So if you're in an airplane, that's how you would do it. You would go up so many, usually we go off the north line, but here we're going off the east line. So many east, so many degrees north, and then go out there so many miles. And that's how we get to that point. So now we have to decide how can we write these, this r and theta. So this is going to be equivalent. We're going to put the r first and the theta second. So now the theta can be either in degrees or radians, and we'll start out with degrees, but each problem we'll have to decide that. Now what we want to do is we have polar coordinates and we have rectangular coordinates. We need a relationship between them. What's the relation between the x, y's and the r thetas? So we can translate from one to the other. And in real life, this is how we do a lot of math. We say, boy, the problem's really hard to do in rectangular coordinates and maybe impossible. So then what we do is we convert over to polar, problem's easier or even able to do it, and then convert your answer back. So we translate into another language just to do the problem. This happens all the time in engineering problems, in statistical problems, where you can't do it in one language, but you can do it in the other. So this is kind of your first really nice look at that. And so I want to find a relationship between these. And everybody can figure that out. You already know everything you need to know. We're not going to do anything new today. We're just going to build these relationships up, and we'll write them down over here. So think of a relationship, any equation you can get with an x, a y, and an r and a theta in it. And just build on that. Now, I wished I could ask you and you could tell me, but I can't, so I'll have to tell you what you're thinking. And what you're thinking is, this is a right triangle, so we know a relationship between x, y, and r. And that's the what? The Pythagorean Theorem. So we do know that this relationship exists. X squared plus y squared equals r squared, where r is polar, x squared and y squared are rectangular. So you see how we got a relationship between r, x, and y. Now, do you see any other relationships? Any other connection between them? Well, this is a trig section in pre-calc, so we could use our trig functions. What about the sine of theta? The sine of theta, what's that equal to? The sine of theta equals what? Sine of theta equals y over r. So that's one. Now, it's pretty obvious what the next one would be, the cosine of theta. What's the cosine of theta equal to? X over r. Cosine would be x over r, and is there, well, there's a third one, isn't there? Tangent. The tangent of theta is equal to y over x. So we used up all of our trig relationships. We used up our Pythagorean theorem. We don't have any other relationships in a right triangle between the sides and the angles. So those are all three of them. Now I kind of like to make those look a little nicer than that. And the way I like to do that is, even in this one, we have polar. Oh, we got to have an R down there, don't we? So we got to change that. So now we can have, we've got polar, polar, and rectangular. So if we kind of simplify this by multiplying both sides by r, we would end up with this relationship, that y equals r. No, that's not right. I was right the first time. So this has got to be an x. So this one's clean. Rectangular, rectangular, polar. That's fine. These two we can kind of make a little bit, look a little nicer. We could have, multiplied by r, we'd have y equals r sine theta. So I'm going to replace that one up here. That y equals r sine theta. I'm going to replace this with, by multiplying both sides by r, we're going to get x, r, let's see, that we're going to get x equals r cosine theta. And I'm going to flip this one around a little bit here and put the x and the y over here. And it's the opposite, y over x equals tangent of theta. The only reason I'm mucking around, switching them, over here we have all rectangular language. Over here we have all polar language. And so we have like a little translator with all of those to translate from one to the other. But never forget about this simple little picture. The picture will tell you how to do every single problem. So if you can't think about how to use those, go back to the picture, and the picture will tell you. Now let's take a look at 4 problems that are tied in to using these relationships. Remember, if you're looking at a problem you don't know what to do, draw this picture. I'm going to erase it, and then we're going to take a look at these 4 problems and see. First thing we want to do is we want to convert 4 pi over 3. Now, is this in polar or rectangular? If you're not told, you got to kind of use your own imagination here. Pi over 3 is probably not how far up you want to go. It's probably an angle. Now, if this was in radians, it would be a little bit harder because it'd just be a number. If it was in a, if you actually divided 3 into pi, or you could put degrees in. Now remember, this is the same though as 4, and what's pi over 3? Pi is 180, so divided by 3 is 60. So those are the same. Now if it's like this and had degrees in it, you'd know for sure I'm in polar, aren't I? So I want to convert to rectangular. So I'm going to convert to rectangular. Now it'll always tell you in the directions, but if not, you'll have to analyze that this must be in radians, that in degrees. So now how are you going to convert that over to rectangular coordinates? Well, if you look up here, you can figure it out. Let's see, I want an x and I want a y. So where can I get an x and a y? Well, here's an x and a y. So let's go after the x first. How do you get x? X is equal to r, in this case 4, times the cosine of, I'm going to use 60. And we can figure that out. The cosine of 60 degrees is 1/2. So 4 times a half is 2. So we found our x. It's 2. So now to find the y, we could go over to our formula. Y equals r sine theta. So it's 4 times the sine of 60 degrees, and that's 4 times the square root of 3 over 2. These cancel, so you end up with 2 times the square root of 3. So our y is 2 times the square root of 3. Now, so you could go over 2 and up this number, or you could go 30 degrees and out 4, and you're going to end up the same place. You might want to actually try that on a little graph paper, figure out what this is. Let's see, that's about 3.4. So you're going to go over 2 and up 3.4, or you're going to go up 60 degrees and out that far. But we did convert from polar to rectangular. So now let's just convert the other way, convert over to polar, and try problem number 2. There's 4 problems altogether. Whoops, we don't want to. So let's try converting this time, number 2. Convert. And this time to polar. 12, 5. 12, 5. Let's try that one. Now, can we use our formulas to figure anything out here? Well, we could find our r, because we do know the x and the y, and we could find our r, and then once we knew r, we could figure out our x and our y here, we could figure out our angle. So we can either use the formulas, or let's just say I have a fallback position. I'm just going to draw a quick picture, because I kind of like a picture. And this says I go over 12, and I go up 5, and I want to find this angle and this r. Now you should be able to do that just from the work we did in the last section, and then we could just figure it out. We could figure out that we could use the Pythagorean theorem to get that. That's what that is. So it would be the same problem. 12 squared plus 5 squared equals r squared. So 144 plus 25 equals r squared. 169 equals r squared. So r equals 13. And then to find our angle, we can use, now that we knew that, we could use any of them, but I would use tangent. So we know that the tangent of our angle is the opposite over the hypotenuse. That's this formula. And so now to find theta, we find the inverse tangent of 5/12. So to find the inverse tangent of 5/12, we'd have to leave it like this, or we use our calculator. And we're going to use our calculator to find this in degrees. So let's go to our calculator. And we need to find the inverse tangent. We'll clear it out. Find the inverse tangent. And in this case, we wanted to find the inverse tangent of 5 divided by 12. And we are in degree mode. So that's 22.6 degrees. So now what are our coordinates that are equal to this in polar? That would be equivalent to our r, which is 13, and our degrees, which is 22.6. But just to kind of go back over that a minute, let's see let's see if it kind of looks about right. Just a rough idea. So we've got this. We're going to go over 12, 5, 10, 15. So we're going to go over 12. We're going to go up 5. So we're going to go up here, about there. So that's 5, 12, 5. Now how are we going to do it over here? We're going to go out this angle. Does that look like about 22.6 degrees? Well, if there's one of these, another one of these, they got it up to 90. It looks like it's less than 30, so that's probably about right. And does this look like it's 13 long? I think it does. If this is 12, that looks longer than the 12 here. So it looks pretty close to be that we could go out 12 and up 5, or we could go up 22.6 and up 13. So those are the two ways of converting. So you'll try those and we'll see how that goes. We've got 2 more problems to do, and we'll be done with this conversion thing. I keep wanting to erase that for some reason. Now the next 2 problems are that part that I said was kind of important why we did this. It's especially when you get to calculus. Now, if we have this equation, and you ask yourself, oh, I did erase another one. If you have this equation, and this is in polar coordinates, and our calculator will graph polar coordinates, and you can try that. But let's convert this over to rectangular to see, maybe we want this back over into rectangular. So how can we convert this over to x and y's? Well, now we're going to use these formulas blindly, just manipulate them. And that's really what Albert Einstein did. Albert Einstein was a physicist, but he never did a physical any type experiment. He did everything mathematical, taking the formulas of physics and manipulating them, and that's how he discovered everything that he discovered, which was a huge breakthrough even to this day in a lot of ideas. So we're going to do that same idea. We're just going to manipulate. Now let's see, we've got to replace r's with x's and y's, and all I ask you to do is to replace it. Where can you find an r to replace it with x and y's? Well, here we have an r squared equals this. So if r squared equals this, what does r equal? Well, if you take the square root of both sides, you can see that r equals the square root of that. So we could replace this with the square root of x squared plus y squared. Now, what about this cosine theta? That's a little trickier. Well, the only place we have a cosine theta is here. Let's see how we could change that into x divided by r. If we divided both sides by r, that equals cosine theta, doesn't it? So we could replace this with x over r. There, did we get to where we wanted to be? We got rectangular, rectangular, but we still got polar, don't we? So now let's get rid of the polar. How can we get rid of the polar? Well, we could do the same thing. R equals the square root of this. So this is the square root of x squared plus y squared. And now we did it. And technically we're done. But it's sure kind of messy. So let's multiply both sides by this common denominator. I think that'll make it look a lot better, because it will get rid of a fraction. And a square root times the square root of the same thing, they get rid of each other. So you get x squared plus y squared. Here they cancel, so you get x. So this is our rectangular formula that'll give us the same thing as that. Now we can change this a little bit. Subtract x squared from both sides, take the square root. That would actually be kind of prettier. So we could go, but you don't have to do this. It'd be x minus x squared. Then take the square root of both sides. Y equals the square root of x minus x squared. And that'd have to be plus or minus. So that's kind of the prettiest one, but I accept even this original one, as long as you get rid of the r and the thetas. And that's what we converted. So now let's convert back the other way. Now if you were to graph this on your calculator in rectangular coordinates, you'd have to do this twice, one with the plus and one with the minus, but then you'd get the same very unusual look that we practiced later in class. Let's do one more the other way. These are not hard, even though they look messy. In fact, they're an easy way to, you should get these all right. People sometimes are intimidated. And so once they're intimidated, they say, well, I don't know, it looks kind of complicated. But let's just see, all we're doing is really not thinking here. We're just plugging in. So now we're in rectangular, we want to go to polar. What could we do here? Well, there's a couple ways to do it. I guess since I just want to get credit, I'll look at x squared and figure out where we got an x squared. I'll look at y squared and figure out where we got a y squared, and I'll leave it at that. So let's see, where do we have an x squared? Well, we got an x here. If I squared both sides, then x squared equals r squared cosine squared theta. So I could put that in place of this, r squared cosine squared theta, the 2. Now I could do the same thing with the y. So this would be r squared sine squared theta equals 8. I'll give you credit for that. Now in this one, we like to get the r by itself so we can graph it. And could we get the r by itself? We could factor out an r squared on this side. This is messy looking. There's nothing pretty about this. So now let's see, we could divide by this thing, divide both sides by that, and you're going to end up with 8 over cosine squared theta plus 2 sine squared theta by multiplying this side by this and that side by that. They cancel on the one side. Now to get r, we would take the square root of the other side. Now that's a messy looking thing, but your calculator actually knows how to, and I didn't do the real easy ones here. Some of those are in the homework. So that we actually did it. But once again, if you do this, I give you full credit for it because you accomplished it. This was an x and y, this is an r's and thetas. But if you actually wanted to graph this on your calculator, you'd have to use this form because it's in r equals something, just like our other ones are y equals something. So we convert it over into a different language. Sometimes things convert real easily. The circle is probably the best example. And let's just take a quick look at the circle, because the circle is very, in our system, looks like that. And it's really kind of complicated to do a lot of calculus with it. But what about in this system? Well, you could replace this with r squared. So r equals 3. That is really easy to work with. So in polar, real easy. In rectangular, not so nice. So some things convert nicely, some things don't. But try the video homework and converting all 4 of those kinds of problems and you'll be all set. Thank you.